Hello everyone, I'm Cristina, and in this video we'll learn a few ways to solve the Crack Me exercise from the Mobfuscator project. In the previous episode, we saw how the tool works and how to use it to compile a reverse shell written in C. We generated a fully functional reverse shell written with only mov instructions. Pretty cool, right? The Crack Me is a simple C program that was compiled with the second version of the Mobfuscator. It expects a key and prints a message accordingly. Something like this. When analyzed in IDA Pro, there's not much to see because everything has been converted into mov instructions. Regarding imported functions, we see printf for printing messages, fgets to read the input string, exit to terminate the program, and sigaction. We'll see later how it's used. We can see the message corresponding to the correct key and the one for the wrong key. Not much else, really. One method to solve this Crack Me has been presented by the author of this blog post. Good to read. He basically supposed that the exit function is probably called for each letter position that doesn't match the correct letter in the password string. So, if the letters are compared one by one, when there is a mismatch, the program will terminate. Based on this observation, the author created a Python script to count the number of instructions executed by the program for each possible letter in each position. The one with the most number of instructions executed must actually be correct. This makes a lot of sense, and the script he shared works fine. It is based on the perf tool, which is present on most Linux platforms. The problem is, inside virtual machines, this doesn't actually work. Let's try. On this Kali VM, I'll run the perf tool. The VM has support for CPU performance monitoring counters enabled. Use almost the same command line as in the Python script. As you can see, 0 instructions reported. That's because this relies on some processor features that are not fully emulated in the virtual machine. On a physical machine, it will look something like this. I have tested and pre-recorded this on a separate machine. The script was executed on an Ubuntu OS version 16.04 with kernel version 4.4 and perf version also 4.4. The Python script is exactly the same and when run, it will find the correct letters one by one. Something to mention here is that the password is not case sensitive. We'll see that the next solution finds a password all lowercase. So that's how it would work using perf tool. Since I couldn't use this processor feature to count executed instructions, I found a different way to do it, using the pin tool from Intel. Pin is a very powerful binary instrumentation tool. We can get its source code and easily compile additional modules. To be able to count instructions, we need to compile the inscount0.so module. A few tricks are needed before because I'm on a 64-bit virtual machine. I need to recompile the libraries for 32-bit because CrackMe1 is a 32-bit ELF file. Let's check. By default, the ins.count module source code is located in this folder. We can issue the make command and it will compile the 64-bit versions of all the example modules in this folder. See here in the output objects folder. We have the 64-bit versions only. To compile for 32-bit, we need to specify the -M32 flag and also make sure to use the correct corresponding include header folders, like these ones over here. I already modified the commands accordingly. The first one will generate an object file .o and the second one will link it to generate an SO library. Now we have the 32-bit SO file that is needed. The new crackmesolver script uses the pin tool with the ins.count0.so file for 32-bit platforms. When running it, we'll see right from the start that it's a lot slower. Don't worry, we will see another method that's almost as fast as the initial one in a minute. Same as before, the script runs the binary and counts how many instructions are executed for each letter position. Pin prints to an output file which we need to open and read. This takes a lot of time. When a letter is correct, the number of instructions will be significantly greater. If you observe here, for all the letters the instruction count is the same, and we will see that when we reach the first correct letter, the instruction count will be higher. We'll let it run for now and come back to it in a moment. I found another method which I wanted to show, which relies on a different observation. After watching the presentation of this tool, I learned that it uses two signals for key functionalities. We've seen them in IDA Pro. The signals handlers are configured using SIGAction. The two signals are SIG-SEGV and SIG-IL, corresponding to a segmentation fault and to an illegal instruction being executed. Mofuscator uses SIG-SEGV to execute a function and SIG-IL to execute a jump instruction which jumps to master loop. A move to the EIP register is invalid in x86 assembly. Because of this, the author needed a trick to change the instruction pointer, EIP. Before continuing with this, let's quickly check up on the instrumented binary and see if it works. Notice that the instructions count is constant until we reach a correct character, which triggers extra operations. When encountering a wrong letter, the program simply terminates. Let's give it a few more seconds. It has to iterate through the whole printable ASCII character char set for each position. Running the instrumented binary is way more slower than running the native one that relies on the processor performance counters. There is a way actually to speed it up a bit by modifying the source code from ins.count0.cpp to replace printing to a file with standard output. Okay, notice that when we reach the open curly bracket character, the final instruction count increased a lot. In the next iteration, this letter will be used as the first character of the key. Very neat trick, and we don't need to do any disassembling. This is called side channel analysis. Give this script a bit of time and it will find the full password. Let's switch back to the other method that I started to talk about. I mentioned that the jumps are performed using the sig-il signal. Let's have a look. Run the CrackMe using strace tool and provide first an invalid character. We can see that there are 3 jumps after reading the first incorrect letter, plus a function execution using sig-sev. For another wrong character, signals are exactly the same. But if we provide the correct one, there will be an additional jump. We have 4 sig-il signals now. Based on this observation, I put together a short bash script that executes strace, grabs for the total number of sig-il signals, and then gets the maximum for each position. Let's run this script. For each character, it prints the number of jumps. On the first position in the key, there are 4 jumps for every character except the correct one, for which there are 5. To make it run faster, comment the printout. Now it quickly finds the first character, the second character, and so on. It's not as fast as perftool on a physical machine, but is definitely a lot faster than the binary instrumentation. To recap, in this video, we've seen 3 ways to solve this CrackMe. The first one relies on the perf tool and processor performance counters to monitor instructions count. Unfortunately, this didn't work in a virtual machine. The second method achieves the same thing, but is based on the pin binary instrumentation tool from Intel. The third method relies on the observation that jumps in Mobfuscator are performed using the sig-il signal handler. This one already finished, so let's try the password out. Looks like a correct flag. Okay, as expected. Out of curiosity, let's check if it's case sensitive. If you remember, the script based on perf found a slightly different one. Thank you very much for watching. Let me know in the comments if you find other interesting ways to solve this. If you like this video, please subscribe for more weekly videos. Cheers!